session of the day on zero knowledge, Oblivious transfer, and key management. Our first talk is on tight security bounds for Mikali snarks, and this is a joint work by Alessandro and Elon is going to give the talk.
Yeah, hi everyone. Let me first just apologize. I lost my voice yesterday and I just found it, but like half, okay. So I'll start the talk. So this is tight security bounds from Mikali snarks. Okay, so the subject is going to be succinct non-interactive arguments in the random oracle model. So let me just very briefly remind everyone what I'm talking about. So these are snarks. This is going to be a proof system. It's a non-interactive proof system for some language L. We have a prover and a verifier. The prover sends a single message pi. And the goal here is to really get a succinct communication. Okay, so this message is going to be very small, in particular, much smaller than just sending, let's say, the NP witness. And the way we're going to do this is by relaxing the soundness to be computational. And in the random oracle model, so I'm just going to define this slightly more precisely. So the prover and verifier share this random function in the sky, okay, this random oracle. And we define T epsilon security if for every X not in the language, and for every T query unbounded adversary P, the probability that this unbounded adversary that performs at most T queries talks to the random oracle and outputs a proof pi that convinces the verifier that interacts with the same oracle is at most epsilon. Okay, that's just definition of snarks in the random oracle model. Okay, so why do I focus on the random oracle model? There are a lot of snarks in the standard model, but really it's a very elegant information theoretic model. We have very beautiful constructions, and I'm going to slightly talk about Mikali. Of course, once you have a construction in this model, you can heuristically, instantiate the random oracle using some relatively lightweight crypto. And as a result, what you get is this is a very nice way to get fast, okay, so like fast schemes where the prover and verifier are quite fast. They are plausibly post-quantum secure, and they require no trusted setup. Okay, so these are snarks and DOM. Now I want to focus on maybe the first and most popular snark and DOM, Mikali's construction. I'm not going to go in all the details of the construction. I assume you guys at least heard it. But what Mikali did, he said, okay, let's take a PCP, okay, and let's commit to a PCP string for the language using a Merkle tree. Okay, that supports local opening. And then using the fiat Shamir, we're gonna derive randomness for the PCP verifier and just give all the PCP answers along with the authentication passes in the tree. And this is the snark. And what is the soundness that we get from this scheme? So I have to use some PCP. So let's say it had error epsilon PCP. Then the best soundness error that we know due to BCS is this epsilon arg, which is going to be T times epsilon PCP. Okay, so we have the error of the PCP, and the cheating prover can try T times to attack this. Okay, so this is when we have this. Or he can try to attack the random oracle. Okay, and in the analysis, you want to assume that he didn't find collisions and stuff like that. So you get this T squared over 2 to the lambda, and this is due to the birthday paradox. Okay, and one question is this tight? Is this expression tight? So this part is actually tight. Like if you really have an error of epsilon PCP, he can try T times, okay, because this is the budget the adversary has, and so you actually get this error. But this part, it's very unclear if it's tight, okay? In particular, this was used to assume that he didn't find any collisions, but if he has one collision, does this mean that he can attack the scheme? So I'll just mention that a negative answer to this question is good news, because if this is not tight, then we can actually prove something tighter and we'll get better security, which means a smaller argument size. Okay, so before I tell you our results, let me just pinpoint the question. So the actual answer slightly depends on the fine details of the construction. So if you're slightly careless with the implementation, actually a single collision is very harmful. So if you just use, let's say, a binary PCP, okay, and you do nothing, you just hash everything, let's say a binary PCP padded to the length of the random oracle, then you can actually use a single collision between 0 and 1, okay, in the leaves, and you can just reuse this collision for the entire, for all the leaves. And then actually the adversary is like, he's not committed to anything. Like every leaf he can open to 0 or 1, which gives him like full power. Okay, and then the soundness is optimal. But this can be trivially avoided if we just added prefixes. Okay, if we just add prefix to every query. Okay, so when he hashes here, we just add the prefix 1, and here 3, 1. Okay, this means that any collision here is just not useful here, because the collision here would have a different prefix, so he would have to work again. And now with this domain-separated version of Mikali, we can ask, is this optimal? And our main result is that a negative answer, this is not optimal, and we actually give a tight security bound for Mikali. So the soundness is this thing that we said that is already optimal, plus some small expression C, okay, which is this, let's ignore this for now, T over 2 to the lambda, okay, where the previous analysis said that we needed T squared, okay, over 2 to the lambda. And this expression is tight, we show a matching lower bound. So the implications is if you want T epsilon security, before you had to set the random oracle to be log T squared over epsilon, okay, to get T epsilon security, and the argument size depends on this lambda. And using our analysis, you can set lambda to be the max of these two expression. Let's focus, let's say, on this one. So which one is bigger depends on the actual values of T and epsilon. So you can just use lambda to be log T squared instead of log T squared over epsilon. Okay, and the argument size is roughly Q. Q is the number of PCP queries times lambda times log n. Okay, so these are paths. Every path has log n nodes, and node is lambda bits, and you have Q of them. It's not only a theoretical result, it actually gives concrete benefits. So we really worked very hard on the constants of these theorems. So you can see we compared our analysis with the standard analysis of the Mikali on some standard PCP that we repeated, and you can see the gains that we get as a function of T and epsilon. So between like 20 and 40% improvement. Just one quick slide on the proof. If the prior analysis said, how do we get security for Mikali? We just assume that the prover found no collisions or inversions, and this cost us in the probability. Okay, so we had to condition on this event. And once you did that, you could just reduce back to the PCP soundness. What we do, we actually we cannot just stop the analysis once he found the collisions. We're gonna score how many collisions and inversions he did. And we give a probability for each score. And then we reduce it to a different game that we introduce, a three-soundness game. And we reduce this game to a very simple but more stronger in the PCP reverse soundness game. And this one we build from PCP sounds. Oops. Okay, sorry. Yeah, so that's it. I'm done with this.
Thank you. Do you have any question for Ilan? All right, no questions from the chat. All right, thank you so much, Ilan. Next talk is fully succinct, publicly verifiable delegation from constant site assumption by Alonso and Alexandros, and Alonso is going to give the talk.
Okay. Hello, everybody. I suppose you can hear me?
Yes.
Okay, so let's start with this. So this work is about delegation, and in a delegation scheme, we have a verifier which has some heavy but still polynomial time computation. And this verifier would like to delegate this computation to a more powerful, but also still polynomial time prover. Okay, so the computation here is some circuit which on input X should output Y. Okay, so the prover has more time and do the computation and also produce some proof, which is sent to the verifier, and the verifier checks the proof, and checking the proof will convince the verifier that the computation was done correctly. But importantly, it must be much cheaper than just evaluating the circuit. Okay, so so in other words, a delegation scheme is a snack for P. Okay, so we can compare with other constructions, for example, a snack for MP. We can start with something which is very interesting in practice because it's quite efficient, such as growth 16. So it's a snack for any NP statement. And it's attractive because the size of the proof is what we call here fully succinct. So the size of the proof is just a constant number of groups of elements in a bilinear group, and verification is just a constant number of pairings. But the problem is that the assumption is non-falsifiable, and indeed, so you need a non-falsifiable assumption for a snark for MP. If you want to avoid non-falsifiable assumptions, so you need to reduce the expressivity, and you get some kind of, so you start to work with delegation. And for example, we have the work of Kalaipa and Yang at stock 19, where they get a better assumption. So you don't have a non-falsifiable assumption, but a Q assumption, an assumption that grows with the size of the problem. But now the size of the proof is not fully succinct, but grows a little with the size of the computation. Okay, we also have the work of Panet and Rotlund, which is so this work is based on this one and has another assumption which is based on obfuscation or multilinear maps. Okay, but the good thing is that this is based on non-falsifiable assumptions. Okay, but still we would like to have something like growth 16, but based on falsifiable assumptions. And the only thing that there is in the literature, like which is like that, is what is known as quasi-adaptive non-interactive zero-knowledge proofs, and they have similar proof size and verification time. It's based on very good assumptions, so basically on DDH or the lean. But the problem is that the expressivity is quite low. It's just for linear languages and some very specific quadratic languages. So what we do in this work, we take QNSEQ, and using these techniques from this work and some other works, we extend expressivity until we reach P, and we get a delegation scheme. And our approach is as follows. So we start, our building block is going to be QNSEQ because they have what we want. So we want a very short proof size, and also verification, a very good verification time, and be based on constant size assumptions such as DDH or the decisional even assumption. And we use the technique of Panet-Roblum, Kalaipa and Yang of no signaling extraction, and and we combine these techniques with QNSEQ so that we can get this argument with no signaling extraction with good proof size and good assumptions. And we use the technique to build a delegation scheme, but for bounded with circuits. Okay, and so and we get a delegation for bounded with circuits from the lean. And to get delegation for any circuit, we use also our work from Extractors 19, which is delegation for bounded circuit, which has some limitation, was based on Q assumptions. And we extend these techniques to be based on constant size assumption. And from that, we are able to build fully succinct delegation from the lean and with with fully succinct proofs and verification time. And we proceed as follows. So we start from a very, very high level overview. We start from a circuit, and we use our techniques from Extractors 18 for compressing the circuit, so kind of compressing the width, and we end up with some proof which grows only with the depth and not with the width of the circuit. And then we apply the techniques of Kalaipa and Yang. So, and we adapt also the techniques to be based on constant size assumption, and we basically give a proof for this statement. And now we end up with a very short proof for this whole circuit. And this is the picture.
Thank you, Alonso. Any question for Alonso? Okay, so we have no questions from the audience. Okay, thank you so much, Alonso, again for your talk. Next paper is Unexpected Polynomial Runtime in Cryptography by Michael Kloss. And Michael is going to give the talk.
Can you see the slides?
Yes.
Okay, thank you for the introduction. I'm going to talk about expected polytime in cryptography. And so why do we care about expected polytime in zero knowledge? So the reason is that we know that we cannot have strict polytime simulation for constant round black box zero knowledge with negligible soundness error in the plane model. And that's the reason to relax simulation to expected polytime simulation, but still keep the verifier strict poly. Now, this kind of breaks the promise of zero knowledge because the verifier cannot actually run the simulator in its head anymore. And also we run into composability problems because if we apply a simulation to an adversary, we obtain a new adversary, which is now expected poly. So we cannot run a simulation on this again because we cannot handle expected poly adversaries. So what we try to do now is we try to deal with expected poly adversaries. The first thing is we actually have several possible definitions of what it means to be an expected poly adversary. And the definition we use are what we call designated adversaries. That is an adversary which is efficient in the protocol it is designed to attack, but not necessarily in any other context. So this is a very natural definition. With strict PPT bounds, you usually just assume that the adversary will be efficient in any context because you have this strict bound and you can just say it will never run longer than poly steps. But without this strict bound, you need some way to say how efficient it is and when it is efficient. And we use this very admissible definition. So now let's look at why things go wrong when we try to deal with designated expected poly adversaries. And for this, we look at this very simplified example. So we have this algorithm A, which computes the identity by first sampling a long random string. And if the string happens to be all zeros, it will return X. Otherwise, it will also return X. Now, clearly, A is efficient. And this variation B does the same, except it will loop forever if this random string is all zeros. And clearly, B is not efficient. B is not strictly bounded. B is not even expected poly. But is B really not efficient? So if you want to use A or B as a subroutine, you would only care about the I/O behavior and the resources these routines need. And the resource we care about is time. And well, as black boxes where you can see how much resources they use, so as timed black boxes here, these are actually indistinguishable, at least for poly many tries. And well, this is the core problem we run into. Indistinguishability does not preserve efficiency. And we actually just saw that statistical indistinguishability does not preserve efficiency. And this raises the question, if an algorithm is indistinguishable from efficient, isn't it efficient? And this is the core idea which inspired our relaxation of expected polytime. Namely, we define computationally expected polytime. And for this, we just need to clarify a few things. Namely, what do we mean by runtime? A runtime is just a family of random variables. And what is expected polytime? Well, expected polytime just means that the expectation of this family is bounded by a polynomial in the security parameter. And here we only have asymptotics in the security parameter, nothing else. Now, computationally expected polytime, or CEP, is defined as follows by a few equivalent conditions. So T is CEP if there exists a runtime S, which is perfectly expected poly in the usual sense, and T and S are computationally indistinguishable. So what I mean here is PPT distinguishers. So the distinguisher has bounded runtime, and it actually gets repeated access or poly many samples. We could also allow CEP distinguishers here, but then the definition gets kind of recursive. And this is also equivalent to allowing statistical indistinguishability, which means poly-many samples, but unbounded runtime for the distinguisher. And this is equivalent to another definition, which says that there exists a set of good events which has overwhelming probability, and conditioned on this set of good events, the expectation of t is actually bounded by a polynomial. So in particular, this last point says that sept is very close to the usual EPT notion, whereas the point 1 says that you can, under indistinguishable transitions, you preserve sept. And with this, let's come to our contribution. So we define sept, this relaxation of EPT. We provide some basic tools for obtaining efficiency from indistinguishability. Namely, we provided adaptations of the usual standard reduction, so a direct reduction, and the hybrid lemma in this setting of designated adversaries. And we show that we can now handle designated sept adversaries in sept. So we have symmetric runtime classes for simulator and verifier, or adversary. And finally, let me note that we do pay a price for these nice properties, because if you cannot rely on these basic tools, arguing efficiency can be quite hairy. So thank you.
Thank you, Michael.
Hey, I have a question.
Yes.
Yeah.
Can you go back to the slide with all the definitions?
Yes. So,
Just
yeah.
Yeah. So you could also have a definition where you have this bad event and condition on not bringing the bad event. The running time is strictly polynomial.
Yeah, you can define a computationally strict polytime. You mean?
No,
Or...
I mean like equivalent to definition 3, only where instead of expected, instead of the expectation of TK, I want to say that TK given GK is strictly polynomial.
So PPT.
Yeah.
Strict poly, and a bound on the supremum. Yes, you can do that. And
so I was wondering like if...
But actually there's a prior work whose techniques I also use by Hofheinz, Unruh, and Müller-Quade, which calls that notion, or a very similar, it's basically this notion. It's called PPT with overwhelming probability, I think. Does this answer your question, or?
Yeah, I didn't have a real question, just wondering about this definition and where it sits, like in this, you know, between all the equivalents you showed.
Yeah, that would be, I mean, if you use a strict bound here, you would move out of expected time, of course. You would now be a small relaxation of strict time. And actually this relaxation is used in some places. So this Hofheinz, Unruh, Müller-Quade is that one which is most closely related to this work, definitely. But I've also seen it in other places.
All right, guys. Are there more questions for Michael? Okay, thank you, Michael, again. Next talk is amortizing rate 1 OT and applications to PIR and PSI by Melissa, Chase, Sanjam Garg, Mohammad Ajavadi, Jalene Lee, Pihan Miao, and Peiyan is giving the talk.
Thank you. Thank you, Alessandra, for the introduction. Can you see my slides?
Yes.
All right. So we start with the problem of oblivious transfer, or OT for short, which is a protocol between two parties, a sender and a receiver, where the sender has two messages, M0, M1, each of length n, and the receiver has a single bit B as input. And from the OT protocol, the receiver gets one of the two messages depending on his choice bit, namely M sub B, and the sender gets nothing. In this work, we're interested in two-message OT, where there are two messages sent between the two parties. In particular, in the first round, the receiver will somehow encrypt his bit B and send to the sender and keep some secret state. And then in the second round, the sender somehow encrypts her two messages and send to the receiver. And then the receiver can use the secret state to recover M sub B. If we look at the message sent from the sender, which we call OTS, and consider the ratio between the length of a single message M0 to the length of OTS, we know that information theoretically OTS cannot be shorter than M0. So this ratio is almost 1. And in fact, rate half is fairly easy to achieve in a generic way. But in this work, we're particularly interested in rate 1 OT, where this ratio goes to 1 as n goes to infinity. But then you might be wondering why. Why do we care about 2-message OT and why in particular rate 1? Let's look at the example of 1 out of 4 OT, where the sender has 4 messages and the receiver wants to get one of them, in particular M sub BC. So the receiver has 2 choice bits, B and C, and we can achieve a 1 out of 4 OT from 2-message OT in the following way. In the first round, the receiver encrypts his 2 choice bits, B and C, and send to the sender and keep 2 secret states, STB and STC. And then the sender first uses the encryption of C and this pair of messages to generate an OTS message. And then she generates another OTS message using the encryption of C and another pair of messages. And then she will treat these 2 OTS messages as a pair of messages to generate another OTS message using the encryption of B and send to the receiver. And then the receiver can first use STB to recover one of these OTS messages, and then use STC to recover the desired message. So if you think about it, the 2-message OT allows us to do 1 OT inside another OT inside another OT. It allows for nested OT. And the rate 1 property guarantees that the final OTS message is not too much longer than the initial messages. So the extra communication cost only grows linearly in the number of sequential OTs, not exponentially. The 2-message rate 1 OT allows us to do nested OT with low communication. And this leads to more advanced applications where the sender has a large database and the receiver is interested in a particular location of the database, but he doesn't want to reveal this location to the sender. In these applications, we can achieve this much communication, where D is the size of the database and lambda is a security parameter. So it doesn't have to grow linearly in the size of the database, but only logarithmically. And here is a list of more concrete applications, including single server PIR with polylog communication and PSI with unbalanced sets, where the communication only grows polylog in the size of the larger set, and so on. Now, can we achieve rate 1 OT? The answer is yes. The Damgard-Urich crypto system achieves rate 1 OT from the DCR assumption, and a recent work by Doltony et al. In 2019 constructed rate 1 OT from another primitive called trapdoor hash functions, which can be realized from various assumptions. Now let's take a step back and look at rate 1 OT again. So far, we have only focused on the sender communication, which is rate 1. This is the best we can hope for. But how about receiver communication? So if we look at the rate 1 OT construction from DDH, for the first bit of the messages, the receiver needs to send order n group elements. And this repeats for every bit of the messages. So the overall receiver communication is roughly order n square group elements. A recent work by Garg, Hajabadi, and Ostrowski improved the communication from order n squared to order n group elements based on the power DDH assumption. And the high-level idea is to use a sliding window where the first bit uses these group elements, the second bit uses these, and so on. So if you look at the 1 out of 4 OT example, the receiver needs to send 2 OT messages, and each OT message consists of order n square group elements from DDH or order n group elements from power DDH. And in the more advanced applications, the receiver needs to send more OT messages. In particular, n is some polylog in n, polylog in d, and the number of OTs is also some polylog in d. So this becomes more expensive. And in this work, we asked the question of whether we can further reduce the receiver communication to save another polylog factor. Or if you think about it another way, can we somehow reuse some of the elements from the first OT message in the other OT messages to save a polylog factor? And here is what we achieved. So we proposed a new primitive called amortized rate 1 OT, which works as follows. There are two phases, an offline phase and an online phase. In the offline phase, the receiver sends order n square group elements to the sender and keeps some secret state. And then in the online phase, the sender is given a pair of messages and the receiver is given a choice bit. And then the receiver can use the secret state to generate an OT message, and the sender will send back OTS. Then the receiver can use the secret state to recover M sub B. We still require the rate 1 property, but now the communication from the receiver in the online phase becomes only a constant number of group elements. And the online phase is not just a one time, it can be reused for arbitrary number of times. For example, they're given another pair of messages and another choice bit, and they can do this again for arbitrary number of times. Another nice property in our construction is that the secret state remains unchanged throughout the entire execution. And this is crucial for some of our PSI applications. So this is amortized rate 1 OT, and we can achieve this primitive based on the bilinear SXDH assumption, where we assume a bilinear map where both G1 and G2 are DDH hard. And we can further reduce the receiver offline communication to order n group elements based on the bilinear power DDH assumption, where we additionally assume G1 is power DDH hard. And using this primitive, we can reduce the receiver communication in the more advanced applications to save a polylog factor. Or if you think about it another way, there's an offline phase where the receiver sends polylog group elements to the sender, and then the receiver's online communication is reduced by a polylog factor. And this can repeat for arbitrary number of times. So to summarize, we proposed a new primitive called amortized rate 1 OT, where the receiver's offline communication is order n square group elements. And then in the online phase, the receiver's communication is just constant number of group elements. And this can be done from the bilinear SXDH assumption. We can further reduce the receiver's online communication to order n group elements based on the bilinear power DDH assumption. And using this new primitive, we can save the receiver's communication in a lot of applications, including single server PIR and unbalanced PSI and so on. And we have more optimizations in the paper. That's it. Thank you.
Thank you, Pihan. Any questions for Pihan? Okay, so there are no questions. Thank you again. All right, so next talk is ring-based identity-based encryption, asymptotically shorter MPK, and tighter security. This is a joint work of Parhat Abla, Tengar Liu, Han Guang, and Zhendong Wang, and Parhat is going to give the talk.
Wait, thank you for the introduction. Can you see the screen now?
Yes.
Okay. Let me just a little bit. Stop now. Okay. Our paper is about lattice-based identity-based encryption, asymptotically shorter than MPK, and tighter security. I am Parhat Abla. In our paper, our contributions are we constructed a lattice-based IBE with more compact MPK and improved security analysis of identity-based encryptions. The lattice-based IBE with adaptively secure security is firstly introduced in the ABB10 in which the MPK consists of theta lambda matrices, and then there are many improvements. And currently, the most advanced construction is given by Yamada 17, in which the MPK consists of omega lambda, log lambda matrices. But their construction is implicit. That means that we can give concrete parameters for his construction. In our paper, we give a ring-based identity-based encryption in which the MPK consists of omega 1 ring vectors, and we can give a concrete parameters for the IBE. The most important part for the constructing a IBE is construct a partition function and homomorphically evaluate the partition function. So we first constructed a partition function in which we give a basic hash, and the basic hash is this h of z is the ECC of z and alpha, and we choose the alpha's place of the ECC and minus a random element beta, which is in ZP. This is unsatisfied for the partitioning, and we parallelly repeat the basic hash, and we get a vector. This hash function satisfies partitioning property, but we cannot able to construct a compact IBE. So we embed this vector, which is in ZP in each element, and we just embed this vector into the x to the exponent here, and we can construct using this one ring element. We can construct a IBE with more compact MPK. For this, to homomorphically evaluate our hash function, we introduced a new technique. We use the equality test. The equality test is given the encoding of alpha I, which is in Zn, and a j, which is in Zn. It's a clear text. And we want to homomorphically evaluate the equality test of this j and the alpha I. The previous techniques are, firstly, they want to bit decompose the alpha I and bitwise compare with the j. And we observe that in the ring setting, when r is equals to zx over x to the n, and it's a cyclotomic ring, there's a function fv, which is 1 plus v to the m minus 1. And if v is equals to x to the 0, and the sum is equals to m. If v is not equals to x to 0, this is a mistake, and the sum is equals to 0, because the x to the m is 1 and the sum is equals to 0. So if you multiply by m inverse to the hash evaluation of x to the I, so we can partition whether the v is equals to alpha x to the r 0 or not. So if we given the x to the alpha minus j, so we can homomorphically evaluate the function f, and then we can homomorphically evaluate the equality test of this function. So our homomorphic evaluation needs only one ring vector. This is the encoding of x to the alpha minus 1. The previous schemes need log n encoding or a GSW type encoding, because they need a bit decomposition of alpha I. Our second contribution is improvement on the IBE security. The previous techniques are using the with artificial abort technique or without artificial abort technique. If the reduction uses the with artificial abort technique, then the running time of the reduction will increase a 1 over epsilon square addition. And if the reduction used without artificial abort technique, then the advantage of the reduction will lose another epsilon. Our security analysis improves both with artificial abort and without artificial abort technique. Our analysis needs only 1 over epsilon blow up in the running time if used with artificial abort technique, and only lost a epsilon squared if used without artificial abort technique. To give a better security analysis, we use the bit security framework of Vicencio and Walter, in which the adversary will able to abort the game. If we let the alpha is the non-abort probability and the beta is the conditional success probability, then the advantage of the adversary is defined as epsilon alpha times 2 beta minus 1 squared. So use this framework, we can improve the previous lattice-based identity-based encryptions. The most important thing is analysis game 0 to game 1, where we use the partitioning, and the other games are just use the statistical distance or the assumption of ring LWE or LWE. So in game 0, the reduction chooses a random partitional function h by randomly choosing the indexes, and the reduction may use with artificial abort technique or without artificial abort technique. So, sorry, and we give a important lemma, which is alpha 1, which is the non-abort probability of adversary in game 1 is larger than gamma mean, which is the lower bound of gamma. The gamma is a partitioning probability for the ID star, which is the challenge identity. The hash of ID star is 0, and the other identities is the hash of identity is non-zero. And the beta 1 is larger than the ratio of gamma min over gamma max times beta 0. So if we let the ratio, this ratio is equals to 1 minus delta over 4, then the epsilon 1, the advantage of the adversary in game 1, is approximately larger than epsilon 0 times gamma mean. So if the reduction we use with artificial abort technique, then the ratio is almost equals to 1 over 2. And to increase the ratio to 1 over delta over 4, the reduction samples 1 over epsilon samples. If the reduction used without artificial abort technique, then the ratio is exactly what we wanted, and the reduction loss will increase by a vector of epsilon squared. I note that the previous reductions will need 1 over epsilon squared samples or increase the reduction loss with a factor of epsilon. So we improve both with artificial and without artificial proof techniques. And thank you. Any questions?
Thank you, Bharat. Any question for Bharat? All right, we have no question. Thank you again.
Thank you.
Next talk, we'll take 5 minutes to read the others. It's crafting key trees, efficient key management for overlapping groups. It's a joint work by Joel Alwen, Benedict Auerbach, Mirza Had Baik, Miguel Cueto Noval, Karen Klein, Guillermo Pascal Perez, Christoph Pieczak, and Michael Walter, and Benedict will give the talk.
Thank you for the introduction. So yeah, I'm going to present our paper Crafting Key Trees, Efficient Key Management for Overlapping Groups. And this is joint work with Joel, Ahad, Miguel, Karen, Guillermo, Christoph, and Michel. Okay, I'm going to start with a quick reminder on what key trees are and what they are used for. So the setting we are interested in, we have a group of users who wants to agree on some group key. And this key is then supposed to secure the communication within the group. And we assume this group to be long-lived, so the users want to be able to regularly refresh the key material known to them. This is on one hand to achieve forward secrecy, but on the other hand, to recover from potential corruption. And a tool that is used quite often in this setting are key trees. So this would be a directed tree where the root corresponds to the group key and the leaves correspond to the users. And every node in this tree is associated with a key pair of an asymmetric encryption scheme, where the idea is that a user knows exactly the secret keys of nodes which lie on the path from their leaf to the root. Now, if we assume that one user got corrupted and now wants to perform an update, they could do this as follows. So first, they would simply generate fresh keys for every node on their update path. But then, of course, they have to communicate this change to the rest of the group. So to do so, they would encrypt the new key of a node to the public key of its co-parent. So this would be the parent of this node, which does not lie on the update path. But now users below this node can decrypt, recover the secret key, and then in turn recover the secret keys up to the root. Okay, so the update cost in this case is simply the number of ciphertexts that have to be sent out. So this would be the length of the update path. So if we use balanced binary trees, then this would be logarithmic in the number of users. And such key trees are used in the construction, for example, of continuous group key agreement. So for example, in the current message layer security standardization effort, but also for building multicast encryption schemes. So here one would use symmetric encryption instead. And as we've seen, the update cost per user is logarithmic in the number of users. And this actually turns out to be optimal with respect to the average update cost. Now, in this work, we are interested in the question, what if we have multiple potentially overlapping groups? And in particular, can we find solutions that have a lower update cost than the trivial solution, which would be to simply build one balanced tree for every single group? Okay, so to this end, we introduce key graphs. So in our setting, we have n users and we have k groups, each of which consists of some of the users. And now a key graph for such a system would require one sink for every group, which would serve as the group key. And for every user, we would want to have one source. And now, of course, we have to somehow enforce correctness and security of this construction. And I think it's quite naturally what we require is that there should be a path from a user's source to one of the sinks exactly if the user is a member of the corresponding group. And our goal is to find now graphs which have a small update cost. So the update cost of one user turns out to be just the number of nodes in the graph they can reach. And we're interested in minimizing the total update cost. So this would be simply the sum of the update cost of all users. So, okay, let me spend the remaining time to just give you a very rough idea of our contributions. So we tackle this question in two different settings. The first one is an asymptotic setting. So here we have some fixed system of k groups. And now we let the number of users grow in a way that leaves the relative size of the groups, but also the relative size of their intersections constant. And in this setting, we can compute the optimal update cost of key graphs by first proving a lower bound and then giving a matching construction. And interestingly, as you can see in the table, it turns out that in this setting, this optimal update cost actually does not depend on the particular group system, but only on the number of users. And also, as you can see, we can save a factor which corresponds to the average number of groups that users are members of compared to the trivial solution. But all of this comes with some caveats. So on one hand, this asymptotic effect actually can kick in quite slowly. And on the other hand, those two solutions from the table actually perform quite bad for certain natural group systems. So we also investigate this question for concrete group systems. And there we have two contributions. So first, we propose an algorithm which computes key graphs, which seem better suited for concrete systems. And we then compute bounds on its update cost that make it quite easy to compare it to the trivial and the asymptotically optimal solution. And it seems to do indeed better, but unfortunately, due to some rounding issues, we cannot formally prove that. And overall, I think the question of optimality for concrete group systems is an interesting open question for future work. So this would be something like, does our algorithm always produce an optimal solution, or maybe more general, is it actually possible to efficiently find the optimal solution given some root system? And finally, the second contribution in this for concrete systems is that we derive lower bounds on the update cost of continuous group key agreement schemes and multicast encryption schemes for multiple groups. And we do this in a symbolic model in the style of Dolev and Yao. So here we consider schemes built from certain building blocks. Concretely, this would be encryption schemes, PRGs, and sequence sharing. And we model those building blocks as idealized primitives. Okay, so I hope this gives some idea of what we do in this work. And if you're interested, please check out the longer talk And I'm happy to take questions. Thank you.
Thank you, Benedict. Do we have any question for Benedict? Okay, so there are no questions. Thank you again.
Sure.
Okay, so last talk of the session, computational robust fuzzy extractors for CRS dependent sources with minimal mean entropy. This is a joint work by Hanwen Feng and Qian Tang, and Hanwen is going to give the talk. Hanwen, we cannot hear you.
Okay.
Okay,
Can you hear me?
Yes.
Okay. Thanks for the introduction. Like any random extractor, a robust extractor can produce a perfect secret from a weak secret. It also outputs a public hyperstring, and with it, we can later reproduce the same perfect secret. And this hyperstring indeed generates the seed in conventional random extractor. Regarding security, besides privacy, its additional property, robustness, ensures that any manipulation on this hyperstring will be detected and rejected by the reproduction algorithm. So this primitive is powerful and can serve as a one-message authenticated key exchange protocol from weak secret. And if the weak secret used in the reproduction algorithm can be close but non-identical to the original one, we can call this primitive robust fuzzy extractor. For plain model and information theoretical robust extractors, there is a tight lower bound. That is, if there is the construction working for all secret sources with n bit length and k mean entropy, then the entropy rate k over n must be larger than half, which is sharply in contrast to conventional random extractor that could work for sources with superlog mean entropy. On the other hand, we can get around this lower bound by using a random oracle, or in the more standard CRS model, we have constructions for CRS-dependent sources with minimal entropy requirement. But CRS independence is hard to justify and unnecessarily restrictive. So we are curious, can we have a robust extractor for CRS-dependent sources without raising extra entropy requirement? In this work, we give a negative answer to information theoretical constructions and present a positive answer to computational constructions. And we also extend our solution to the fuzzy case. A CRS model robust extractor can be described by a CRS sampling algorithm along with a generation algorithm and the reproduction algorithm that take a CRS as input. And it's secure if for any source, any university cannot break the security goals with respect to a randomly chosen CRS. In this work, we prove that if it is secure for any unbounded adversary and any CRS-dependent sources, there should be a fixed CRS such that the generation algorithm and the reproduction algorithm with this fixed CRS actually defines a secure plain model robust extractor. So the entropy rate of admissible sources should be larger than half. It means the same lower bound still applies there. Our second result is the computational robust extractor. Our idea is to take the weak secret as the key of MAC and use the MAC to authenticate the seed of the underlying random extractor, such that active attackers cannot change the hyperstring without being detected. However, since the weak secret is used for both for random extraction and for MAC tag generation, the MAC should provide some level of composition security to ensure our construction works. More specifically, to avoid affecting the random extraction, the MAC should provide key privacy. That is, the MAC tag should not leak partial information about the weak secret. And secondly, to avoid being affected by the random extraction, the MAC should be auxiliary input secure, covering the case that adversary already have some auxiliary information about the weak secret. And since we directly use the weak secret as the MAC key, the MAC key should be structureless. And putting all properties together, we define a new MAC primitive called kappa MAC. And in the construction, our idea is to use an auxiliary input secure digital signature scheme as a MAC. But since couple map requires the key to be structureless, we cannot put the verification key as part of map key, but have to put it as a part of the map tag. And consequently, we need to address the following challenges. Regarding unforgeability, adversary may have actual advantage by modifying this verification key. And regarding key privacy, adversary may learn partial information from this verification key. And to address them, we strengthen the cards and the Vakatanadan signature, which is an auxiliary to the secure signature and multiple places. And our final construction can be from NISC and deterministic public key encryption with specific properties. And our construction can be finally based on exponentially hard DDH and other standard assumptions. In our extension to the fuzzy case, we prove that if our couple map additionally satisfies fuzzy unforgeability, it can be used to convert a fuzzy extractor into a robust fuzzy extractor. And more interestingly, we prove our couple map construction already satisfies this fuzzy unforgeability, so we don't need other construction. That's it. Thanks for listening.
Thank you, Wen. Is there any question? All right, looks like we have no questions from the chat either. Okay, so this concludes this session. Thanks to all